Okay. So we want to find the partial of f with respect to y, so that's equal to the partial of f with respect to q times the partial of q with respect to y. So we know that the partial of f with respect to q is z, and then the partial of q with respect to y is equal to x. Or sorry, it's equal to 1. Yeah, 1. So, which is just equal to, so it's equal to z1, which is z, and then the partial of f with respect to x is equal to the partial of f with respect to q times the partial of q with respect to x. So again, that's z times 1 equals z. So does anyone have any questions about this? Okay, so we can just go through the slides and see how we're doing this. We're updating it like this. So
wait, go back a slide. Wait, so you get 1 from multiplying, for example.
So the reason we get 1 is because if we're taking the partial derivative of x plus y with respect to x, then the partial of x with respect to x is 1. The partial of y with respect to x is 0.
Yeah.
Mm-hmm.
But so you have like a red 1 on the right. Where does that 1 come from?
Oh, this?
Yeah.
Oh, that's just because we're doing the partial of f with respect to f, which is just 1.
Oh, okay. And then -4 comes from z.
Because of z, because the partial of f with, because the partial of f with respect to q is z, right?
Okay. And z is -4. Okay. Cool. Okay. Cool.
Yeah. All right. Any other questions? So now that we have this, let's try deriving backprop for some of the layers. Some of the layers we won't get to because they're more difficult, but hopefully we can get a sense of how we might do this. All right, so I'm gonna erase this. So for backprop, so again, we're starting from the back. So let's say for this neural network, we are going to be classifying like digits from the MNIST data set. So like our digits, so that's equal to 0, 1, ... 9. And so when we, so the last thing that we do in forward prop is we want to actually use our loss function. So in this case, we're going to be using a loss function known as the cross entropy loss function, which is and so the reason that we actually get this particular loss function is from maximum likelihood. It's the same principle as when we did it for logistic regression. So if you want a refresher on how we derived this, look at the lecture slides / like lecture video for logistic regression. So basically, what we're going to be doing is we're going to like one-hot encode the labels. So the digit 0, for example, will be mapped to a vector where it's 1 in the first component and then 0s everywhere else to signify that this digit is 0. And then similarly for the digit 9, it's going to map to 0, 0, 1. So we're going to be using this as a way to compare to our actual labels. So let's so essentially what we want to do is, we have our 10 sort of inputs, which is each of these components, and then we're going to be computing this loss function like pairwise with all of the components of the label. So essentially, you can think of that as we're doing like 10 different classifications. Like, oh, did we correctly predict whether or not it's a 0, correctly predict whether or not it's a 1, and so on and so forth. So and so what we're going to be doing is then we are going to so we're going to take like so let's look at this function here L, and we're going to take the partial derivative of that with respect to xi. So we know that if we write all this out, ultimately every term that doesn't include x of I, it isn't going to contribute anything to our partial derivative. It's just going to be 0, right? So the partial of L with respect to x of I is equal to the partial of y sub I log x of I with respect to x of I, which is just y sub I times 1 over x of I. So then if we put all of that into a vector, so the partial of y with respect to x is equal to this vector of partial y sub 1 with respect to x of 1 dot 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 partial of y sub 10 partial x sub 10. So it's just equal to y sub 1 over x sub 1 dot y 10 over x sub 10. And then just as a way to like save notation, we save that as y over x. So does anyone have any questions about how we did this and how we can like say that the partial derivative of this layer works? Anyone? Okay. All right. So now let's move on to a different layer, which we'll do here. So let's consider a layer where we're doing the sigmoid activation function. So recall that the sigmoid function maps, so y sub I is equal to 1 over 1 plus e to the negative x sub I, and it has the desirable property that, its graph looks like this, where this value is y equals 1. So, we can think of it as like a probability measure, which is why, if you remember, we used it in logistic regression. So now let's say, we have, so remember that since this is a hidden layer, there isn't any restriction on the number of inputs or outputs, but so let's just say in the generalized case we have like x sub 1, x sub 2. Oh wait, sorry, I misspoke. So since this is a activation function, actually the number of inputs is the same as the number of outputs. So let's say that this is x sub 1, x sub 2, x sub a. So then that maps to y sub 1 y sub 2, y sub a. So let's think about this now. So we want to find the partial derivative of L with respect to x sub 1. And if we apply our similar chain rule style of thinking, so much like in 6U and A, when they teach you about recursion, you know, they say, like, just trust the recursion. So similarly, let's say that we've already found the partial derivative of L with respect to y1, y2, and, like, y sub A. So then we can just say that the partial derivative of L with respect to x1 is equal to the partial derivative of L with respect to y1 times the partial derivative of y1 with respect to x1. And so if we think about it this way, then okay, so first I'm just gonna label these like activation loss. So you know, let's just say that we've already computed this. Like, you know, let's say that this is right before our loss layer, right? So we can just say that it's equal to that guy that we computed over there. So right now we need to focus on this particular expression, y1 with respect to x1, and, you know, more generally, yi with respect to xi. So the sigmoid function has this nice property that the derivative is y sub I times 1 minus y sub I. So that is the derivative of it with respect to that. So then we can say that the partial of L with respect to x sub 1 is equal to the partial of L with respect to y sub I times y sub I times 1 minus y sub I. And this also brings up another important point when doing neural nets, is that often when you program it, so when you do the forward propagation, let's see if I can find this. So yeah, like right here, for example, like, you know, when you do the forward propagation for each layer, right, you know, you'll have like a vector of results for each of these nodes. Often what you'll want to do is you'll want to save these, because these can be important depending on what you're doing. Because, you know, y sub I is just the direct result of applying this activation function, which we've gotten in the forward layer. So if we save the result, right, then we don't need to compute it again when doing the back layer. So often, like, these y's can be important. So depending on what your activation function is, like, saving it could save you time. So does anyone have any questions about, for the activation layer, how this works? And, like, how we can just, like, stack these together in this way? Okay. So now let's move on to the final layer that we are going to be looking at, which is the fully connected layer. So, you know, this is the layer where we're really going to be updating things. So let's say that I have like x sub 1, x sub a, and this is going to map to y sub 1, y sub b, because, you know, in this case we don't need to have the same number of inputs as we do outputs, and, you know, so we're going to have something like So here we're using the convention. So for W I to j, that means that this is going from x sub I to y sub j. So let's look at this for a. So let's look at this from the perspective of computing the gradient with respect to. So L with respect to x sub 1, because just like we did in this activation layer, we are going to be like passing these backward to previous layers of our neural network architecture. So to do this, so we need to actually figure out how does x sub 1 affect the error. So in this case, it was simple, right? Because x sub 1 only affects y sub 1, but here x sub 1 affects all of these, right? So what we need to do is to find how L affects, to find how x1 affects it, we're actually going to be breaking up into a sum. So it's equal to the, so it's going to be equal to d sub L times d sub y1 times d sub y1 over x1 plus L y b times b x1. And so essentially for this, what we are going to do is we're going to be looking at all of these and summing these up. So let's look at a particular example right here. So with x sub 1, y sub 1. So recall that y sub 1 is equal to w11 times x sub 1 times x sub 1 plus w a sub 1 times x sub a. So the only term where x sub 1 is involved is this guy. So the partial of y1 with respect to x1 is equal to w11. And so then, more generally for, let's say that we're looking at like yb, right? So then, yb with respect to x sub 1, or sorry. Yeah, so yb, then it's like, then it would be like w1b. So we can like collect these as a vector. So the partial so with x1, right, we have this vector w sub b, and which we are then going to be multiplying by this vector of L's and y1s, right? So then, we'll have L1 dot YB. So does everyone see why this makes sense? Okay, so, and then for all of our other x's to xa, we can just make a bigger matrix. I forgot a 1 here. So then we can say that more generally we're taking this matrix W1, 1P, W1, W, A, B, and then we're multiplying it by this matrix over here, so we had L, 1, 1, L, N. So we're not quite done with. Okay, so does anyone have any questions on what I've done so far to get this? So here we're taking the gradients of what we're going to pass backward to our previous layer. Is everyone cool with this? Anyone want me to explain it a step again in more detail? Okay, so now but for this layer we still have one more thing to do, namely, the gradients with respect to these weights, right? That's the whole point, we're training these things. So we need to consider now, for an arbitrary weight, W, ij, right? So what is the partial derivative of L with respect to W, I, J? So essentially for this now, this is actually going to be simpler in some ways than what we were doing over here, because unlike where, each x interacted with all the y's, each w is only going to be interacting with a particular x to a particular y, because that's how these weights work. So now what we're going to be doing is, so we're going to be having, so y sub j is equal to x sub I times w ij. So again, we can break this gradient down using the chain rule. This is the partial derivative of L with respect to y sub j times the partial derivative of y sub j with respect to x of I. Oh, sorry, I mean to say w I j. So here we can see that the partial derivative is just x of I. So we have that. So now essentially it's just for w, right? It's like we can collect a matrix of our w's where this is equal to like w1, 1, w1, j, I1, w, I, j. And so we can similarly collect a matrix of these partial derivatives, and we can say that, we have the matrix that's equal to and so then what we can do is in our gradient descent update, what we do is we say like Wij is equal to Wij minus partial of L with respect to Wij times Wij. This is the real goal of what we're trying to go for here. So Does anyone have any questions on why this is our update? Okay, so, and then, once we get that, then we may have some more layers to propagate, because, some of these neural nets, could have, up to, 50 or so layers, particularly, Raul was saying on Monday when, Google, Facebook, whatever, got into, a pissing contest of who could make the deepest neural net. So, once we finish for a particular, fully connected layer, then given the partials of x's that we collected over here, then, we're going to continue to backpropagate those. So, I hope everyone can get a sense of how this procedure is very modular. We only have to really consider one layer at a time, because we can just trust that for, the previous layer, we've already calculated its gradients, and we can just use those accordingly to update our current gradients, and we can pass that result on in turn. So we only really have this to do. And that's why when you see a lot of libraries out there, like TensorFlow, Torch, Keras, or whatever, it's you build these up one layer at a time, and you can just abstract that way that each layer will take care of what it needs to do. Because oftentimes sometimes when people are inexperienced with neural nets, they may try to put these together in a way which kind of breaks the abstraction barrier, as John De Niro might say, which can lead to some bad results. Yeah, so I guess just one more time, does anyone have any questions about any of this backpropagation stuff that we've done, either our lost layer, activation layer, or fully connected layer? No? Okay. Alright, well, let's move on then. Okay, and so for those of you who are watching the webcast, I'll include a resource which you guys can also look at if you want to see it in more detail or see it with some other kinds of activation functions or loss functions. I just covered one case to give you guys an idea of how this works. So now let's get on to sort of some of the things that you do when training a neural net. So one of the trickiest parts could be initializing these weights. So the whole point of neural nets is to update them and make them the best they can be, but where do you start? So a bad initialization can really screw things up. So let's say that we set all of our weights to 0. So then, depending on our activation function, that could mean that we just pass forward 0. And also, if we make all of the activations for something the same, then in the first layer, right, then that'll just mean that all of our, because we're multiplying everything by 0, then everything that we're passing forward will be the same. So there's no real sense of which features could be the most important. So it's basically just treating everything equally. Then all of our gradients will be the same that we pass forward. So that's not good. We want different initializations. We don't want things to be uniform. So if we look at some schemes seen in practice, so one is to initialize weights, but for each weight you draw from a Gaussian distribution with 0 mean and a variance of 1. And then another scheme seen in practice is doing the above, but then dividing by the square root of the number of nodes in that layer. And this is done to reduce the variance, because essentially it's you want them to be you don't want them to be the same, but you do want them to be somewhat closer together and more tied together. And then there's also this cool thing called batch normalization, which we won't go into too much depth here. I can post a resource that will give you a better sense of how it works. But essentially what we're doing is we are making it so that the outputs of our activation function have the same distribution, and this can help make the initialization less of an issue, because sometimes if we initialize our weights in a particular way, then that'll result in the activations coming from a certain distribution, depending on the distribution of our weights, right? How we initialize it. So if we enforce that all activations have the same output distribution, then that makes initialization less of an issue. So another thing we can get into is updating weights. So recall that, over here we have this particular way of doing it, just based on the gradient, which is also how we did it for linear/logistic regression. But the problem with this method is that it can be very slow, and we want to converge to a minimum as fast as we possibly can. So to do that, what we can use other methods such as Atom, RMS proper, Nesterov, and essentially they're all focused on the idea of momentum, which is saying that okay, for a given weight, we're going to be initializing it multiple times, right? Because we're going to be taking multiple epochs, we're going to have multiple data points, we're going to feed them forward, pass them back, and see how they affect the gradient, right? But it's for this form right here, we only ever consider the current point, but if we considered our previous points, that gives us a sense of momentum, right? Okay, this is the trajectory that we followed currently. So if we're going really well and going downhill, then it's okay, we can just keep going faster because that'll get us there faster. And you can actually see this cool illustration right here of the different sorts of update rules. So you can see that stochastic gradient descent is by far the slowest, whereas a lot of these other methods converge to the star much faster. I'll link to another resource so you guys can actually learn about some of these more in depth if you want to. But similarly, if you want to, you can just call these if you're ever working with a neural net. So does anyone have any questions about what I've covered here, with different sorts of update methods and how, does it at least make intuitive sense why if we consider not just where we are, but previous updates, then we'll go faster? So another thing, which I didn't put in the slides, but I want to talk about is I'll update the slides to include this, but it's known as the vanishing gradient problem. And essentially what that is, so as we're going through the layer, we're accumulating all these gradients in our product, right? So it's we might have the partial of L with respect to one layer is equal to this whole nested sum of products. And let's take a look at this sigmoid activation function, right? So we know that all of the y's are bounded between 0 and 1. So the gradient for that layer will similarly be bounded in this way. So this will produce a number between 0 and 1. So okay, let's say maybe it's 0.5 or something. Okay, so 0.5 isn't too small. But let's say that we're doing this through tens of hundreds of layers. So if we have a bunch of sigmoid activation functions, right, then this could be 0.5 times 0.5 times times 0.5. So this could be 0.5 to the 10, or even as large as 0.5 to the 100. And that makes our gradient really small. So if we're applying any sort of method to update our gradients, then if we have a really small gradient, then we're just not going to be moving. And this can be a problem where you have a lot of layers. So for this isn't as much of a problem for the layers which are closest to the output, because there it's you don't have as many terms in your product, right? It's just this one thing. But as you move forward through your layers, then you'll see how over time these start to build up, right? So all these small things could make it so that then in the earlier layers over here, you aren't able to move as fast as you are in your later layers. So that's what's known as the vanishing gradient problem. There's also a similar problem known as the exploding gradient problem, where if you have really large numbers in your product, then as you go through multiple sort of iterations, then or multiple layers, then those will build up to make a really large gradient, which will then mean that you're moving really fast and you're not stable. So basically the way that we fix this problem is by looking at different sort of activation functions. So recall how over here, it's like we gave different, well, it's not in the slides, but we had the sigmoid activation function, there was the step function. So there are multiple kinds of activation functions that we can use. But one question you may have had is when is one better than the other? And sometimes this vanishing gradient problem can help you determine that. So the sigmoid activation function will give you numbers between 0 and 1, and then there is another kind of activation function called the ReLU, or rectified linear unit, and essentially what that is so you have f of x is equal to the max of 0 comma x, and if you graph that, that has the interesting property where it looks something like this, right? So for x greater than or equal to 0, it's just x. But then for x less than 0, it's just this constant line at 0. So sometimes this can be a better choice of activation function. And then, so it's this is something that you really just have to play around with and notice, if you notice that you aren't training too well, then look at some of your earlier layers and look at the gradients for those and see if they're updating at all, and if not, then you may want to try something else. So does anyone have any questions about that? Yeah?
I guess just in general about gradient descent, how would it deal with saddle points? Is there a way to look specifically?
Yeah, saddle points can be a tricky thing to deal with. So because these loss functions are highly nonlinear and can be in a very large dimensional space, it's hard to know when we have a saddle point or when we don't. So often it's you may just have to trust that it isn't one. And another thing that could help is maybe going through multiple different initializations. When we talked about decision trees in random forest, we talked about ensembling different trees. We can do that with neural nets too. We can try a bunch of different initializations and see which ones do the best. So again, it's if you notice that things aren't going well, then it's you basically just have all these hyperparameters that you have to tune. Again, as Raul said, this is very much an alchemy, not a science. So I'm giving you a bunch of these heuristics for why things could be breaking, but you won't know for sure if it's that. You just have to try and see and hope. And from experience, you'll get to know when things may lead to which problems are more likely to be associated. So yeah, apologies if this isn't very rigorous, but deep learning theory these days is not as rigorous. So yeah, and that's all that I have for lecture today. Alright. Oh shit, did I not record the second part of this? Alright, well. Okay, those watching the webcast aren't going to get the second part of this. Alright, so let's see. So, if you guys want to play around with some more code, let me see. So, for the Kaggle Decal, we have we can use the thing from Monday that we didn't really get to. So here you can see we're making a neural net. Oh yeah, so one thing I forgot to mention actually was the learning rate. So technically this gradient equation isn't quite correct. You have to like also multiply it by the learning rate here. So here we're doing wij is equal to wij minus the gradient with respect to wij times alpha, where alpha is the learning rate. And so what we're doing is we're making a neural network with 2 hidden layers, each of 250, size 256. We have 784 inputs because our image is like 784 or 28 by 28 pixels. And then, we have 10 different classes. And essentially, so we have these 2 things called placeholders here. And essentially the reason that we have them is because as we're running our epochs, we're going to be having different data points and different labels. So essentially this placeholder is just a way of saying this value is going to be changing over time throughout our session, because we're going to be having different features and labels. But we do know that it will be a matrix of floats with this shape. And the reason why it's none is because it'll change with the batch size. Because, we could just take one example and do it. Or we could... Sorry, did you have a question?
No.
Oh, okay. Or we could do it with, say 10 different examples, and then for this, gradient rate here, what we do is we take the average of those 10 examples when we run it. So, that's determined by our batch size, so it's going to be none for right now. And then, it's going to be none by, n input, and then this will be none by n classes. So now we're going to be making a model wherein we have, so we're doing a matrix multiplication here with x, so weights, so h1, biases, b1, and those are defined over here. So, for our hidden layer, we're initializing our weights, from a random normal distribution, as I discussed above as one of the ways that you can initialize. So, this maps from n input to n hidden 1. And then this maps from hidden 1 to hidden 2, and then finally hidden 2 to number of classes. And then for bias, we discussed this in previous lectures where what you do is for your feature matrix, you add a column of 1s so that then for a linear model, right? When you have your biases, that means that you won't just learn planes that go through the origin. So it's instead of just having y is equal to ax1, it's y equals x1 plus b. So for that same reason, we're adding a bias term here. And we're going to be initializing that to random normal. So we're going to do this matrix multiplication here. And then we're going to be passing that through a ReLU activation function. And then we're going to be doing another matrix multiplication. And then we're going to be doing a ReLU again. And then, a final matrix multiplication. And then that'll return a prediction. And then softmax cross entropy with logits. The cross entropy function was the function we used over here. So we're going to be calling that function. So labels will be, y, our ground truth. And then logits, that's going to be our prediction. And then we're going to be training that on an atom optimizer. So if you go over here, oh wait, atom isn't included in this one, but it's another one like these. It's better than stochastic. Atom is the one that people use most these days. So we're going to be training it with an atom optimizer, and we're going to be minimizing cost. Let's see, where is... Yeah, so cost is this output. And so now what we're doing is we're going to be running this session. So then session.run init. So that's where we actually initialize all the variables, because before up here they aren't really initialized. And now what we're going to be doing is, so training epochs, we define that up here to be 15. So for each epoch, we're going to be getting a batch. And then for each example in your batch, you can do, oh wait, so yeah, this is just going to be the number of examples in your batch, and then like there's this special method where you can get a random set of the samples of size, your batch size, and then, so C is your cost, and then you also get out like something related to your model, which we don't really care about, so we're just doing like sess.run, optimize our feedback, and our feed in dictionary where we feed in like, X is our batch of training examples and Y is your batch of training labels. And then, you're updating the cost, and then every so often you're printing out the epoch and the average cost. So here you can see as we're training, right? So our cost starts out about 161, but then through our epochs we get it down to like 0.82, which I don't know about you, but I think that's pretty good, pretty cool. And then what we do is one last time we do it with our test set, because what sort of data scientist would we be if we didn't test things on a different set from which we trained on? So correct prediction, tf.equal argmax pred 1, again as above, we have to take the argmax of the one hot encoding because only one of those things will be 1. And then we're again doing like tf.reduce mean, like we're casting it to a float. And then, so our testing accuracy is 95%, which actually isn't that great for MNIST, but this is a pretty simple neural network. Like, once we get more into like convolutional neural networks next week, then we can get that up to like 99% on our test set. But for right now with a vanilla neural net, we have 94%, which is still pretty good. And then, okay, so does anyone have any questions on this demo, like how we initialize things, like how different things like play in together in this library? Anyone?
What's the threshold for good and bad? Like, good accuracy and bad accuracy.
Well, that's very dependent on this problem. Like for MNIST, because it's a very well-studied data set, it's like the data set to test things on as a baseline. So for a neural network, like 99% or so is like the standard for like industrial standards. Like for a neural network, like I'd say maybe 93% is just the standard for this is better than like anything else. But like among neural networks, like 99% is good. And then for other things, like, it's just sort of dependent on like how well previous things have done. Because like from certain like state of the art problems, like the best you can do on certain data sets is like 60% or something. And it's like a lot of papers are just, oh hey, we tried it and we got it up somehow. We tweaked the architecture a little bit. More hidden layers, different activation function, new weight initialization. So it's like, yeah, it really just depends on what previous models have been able to do and like, how well studied certain data sets are. Yeah, I mean, that's what you were asking about, like, right? Yeah, okay.
Then how do you know you're not overfitting?
I mean, you just have to compare, like, your cross-validation error to your training error. And then, like, to your test error. So, it's like...
Because if you're reading checks or something, and that 1 in a million error happens, and you read an extra 0 or something, somebody's got an extra $1 million or something.
Yeah.
Something like that.
I mean, yeah, that's another thing, too. It's like, what you consider good can also be domain-specific. So, like, I was kind of going under the assumption that you're just trying out on a toy problem.
Okay.
But, yeah, if you're actually trying for real problems, then your thresholds would be more based off of, like, how well you want your model to perform. So, like, I work on, like, doing stuff for, like, gate detection or, like, walk cycle detection. There you want it to be, like, really good. And then it's, like, certain times, like, also it could just be, like, you want to, like, beat what was previously done. And sometimes, but obviously, like, for a lot of problems also, it could be in, like, medicine or something where you want, like, perfect accuracy. You don't want any. And then you could also determine whether it's not more important for, like, a false negative or a false positive. Like, again, like we discussed this before, like cancer diagnosis, right? Like, it could be more important to, like, make sure that no one, like, slips through the cracks and has cancer that you didn't detect. So you can, like, weight your cost function appropriately such that like it gives a different loss for when you have a certain kind of misclassification. So it's like very domain specific and can really depend on like previous things. There's no one cut and dry answer to that question. Anyone else have any questions? All right, well, that's all I have for you guys today. There isn't going to be a quiz again. Hopefully you found this helpful. So yeah, we are good for today. Yeah, and again, the project will be coming out